Now, we're in the chapter of exponential functions, but meanwhile, I want to do a quick recap of what we know about linear functions, because we're going to try to do with exponential everything that we try with linear functions. So let's just do a very brief recap of linear functions. First off, we know what every single graph of a linear function looks like. And here's why. If we actually look at the word linear, we can see the word line in it. That means the graph of every linear function is going to be a straight line. Now, straight lines can only do three things. They can either go up, they can go down, or they can stay constant. Graphs that go up from left to right have positive slopes. Graphs that go down from left to right have negative slopes. And graphs that stay constant, I'll go like that, yes, have zero slopes. So very quickly, the slope tells us an awful lot about the graph. One thing we're going to be looking at a lot with linear functions and exponential functions is data. So what I want to do is summarize briefly what we can do about data, and let's do this with an example. I'm going to write down something like y equals, I don't know, 2x plus 5. We'll look at that. And I want to make a table. To really illustrate what's going on with the table, I don't want the x's to start at 0 and go up by 1. So what I'm going to do is I'm going to have them start at minus 4 and go up by 3 each time. So I'm going up by 3, so I get the minus 1, go up by 3, I get the 2, go up to 3, I get to 5. Now I am going to plug in one number. If I plug in minus 4, I get minus 8 plus 5 is minus 3. Now we can't keep plugging in numbers, but the beauty of exponential functions and linear functions is you don't have to. There's actually a much quicker way if you plan. Now, we know our normal formula for slope is m equals delta y over delta x. But with dealing with data and in calculus, we're much more interested in trying to calculate the delta y's if we happen to know the slope and the delta x. For example, our slope here is 2 because we know this looks like y equals mx plus b. So the delta y here is just 2. The delta x's are the differences between the x values. Well, we know that every time we take an x value and subtract the previous one, we get 3 because that's actually how we constructed this column. So this should be 3. And when I multiply those two together, that says 6. Now, this is delta y. What is that? That's the difference between every y value and the previous one. That's the difference between every y value and the previous one. That's as if you want to start going forward, you need to add 6 each time. So for example, if I add 6 here, I get 3. If I add 6 here, I get 9. Add 6 here, I get 15. I think that works. Let's just check. Here we go, right? When I plug in minus 4, I get minus 3. When I plug in minus 1, I do get 3. When I plug in 2, I get 9. When I plug in 5, I get 15. It works. Yes, and I only really had to plug in one point, and then I had to use the fact that I knew what delta y actually meant, which is really kind of cool. Another way that this gets used with data and linear functions, and this goes even quicker, and we don't actually need the equation for it, right? If we know a function's linear, if we know a function, and I'm going to be using fun is linear, and they just give us 2 points, and it really doesn't matter what. I'll have it going forward. Let's make this, we'll go by 2's here. 6, and how about 2? There we go. Yes, we can make this linear really easily in the following way, right? Just make sure the delta x's were the same as the first one. Now delta x from 4 to 6 is 2, so to get all the other x's, I'm just going to keep adding 2 over and over and over. If this is linear, not only are the delta x's always the same as all the other delta x's, but the delta y's are going to be the same as all the other delta y's. So from here to here, right, the delta y was 2 minus 7, which is minus 5. This says, as I keep moving from one y value to the next, I keep subtracting 5. Subtracting 5, subtracting 5, subtracting 5. Right? And that's guaranteed to be linear data. Now, by the way, if you don't think that's linear, go plot the points in Desmos. You'll see a straight line, which is really, really cool. So we can create linear data just from 2 points, as long as the delta x's are constant, and we keep the delta y's constant. We can tell if something's linear by looking at the data. We can tell by something looking at the graph. We can tell if something's linear by looking at the equation. That's what we know about linear functions. Let's recap what we know about exponential functions as well.